we're going to talk about this morning is mechanical transmission. He had surgery last week. Hopefully he'll be here. Transmission of power, of mechanical power. We'll talk about gears, bearings, roller chains, and belts. So how much y'all know about gears? Huh? We got a lot of things here. Huh? Well, we have a prime mover or something that actually causes things to move. And then somehow we got to transfer from our prime mover over to what we're actually moving, right? You understand? There'd be gears. We'll talk about the type of gears. We'll talk about the terminology or the nomenclature, forces, and design of a gearbox, which is not really important here. So this is some terminology, and this is not all the terms we're going to look at. So a gear is considered to be what we call a toothed wheel, right? You understand that? That engages with another toothed wheel in order to transmit motion. Everybody understand that? And then we're going to use terms. We got what we call the driver gear, also called the input gear. The gear of a gear set. Now, a gear set is 2 gears. And then we have what we call a gear train, which will be multiple gears, right? You understand? So normally we don't have 1 gear without having a what? At least a second gear. That makes sense? So they come in sets of a minimum of 2, and then how many depending on what we need to do to get to the output. So the drive gear in the gear set, this is the guy that transfers the motion of power in the gear set. And then we have the driven gear, right? You understand? Does this make sense? So this is the gear to which the power and the motion is transferred to. Does that make sense? Everybody okay there? The pinion is the smallest gear in the gear set. Very seldom do we have gears of the same size, even though you might run into that. We call the larger gear in the gear set. You hear people call that a gear. And I forgot to put one term up here called a rack. Torque is a twisting force that causes or tends to cause something to rotate about an axis. Everybody okay there? And we'll look at some glossary. There'll be other terms in here. By the way, I updated the glossary, but I couldn't upload it this reason because I couldn't convert it over for some reason. So torque versus speed. Torque, and where the 5,252 came from, I'm not really sure, but it's a constant. And these are different torques. And what you have to understand is that in a gearbox, we're going to do one of 2 things. We're not going to change power. Everybody understand? So if I need to get 50 horsepower out, how many horsepower am I going to put in? 50. Okay, you understand that? Probably a little more. It depends on the efficiency. But just for discussion, we'll say, okay, power in equals power out. Okay, you'll understand that. So what we're doing with gears normally is we're getting the same power, but we're increasing torque or we're increasing speed. So what a gear set does, it either increases torque or it increases speed. But since torque is a representation of force, then so torque is another representation of force. So you got to understand is that what we have to understand is I increase torque, then what's going to happen to speed? Huh? Because torque is the rate of doing work. So what we're saying is that if speed goes up, then torque has to do what? So if we rearrange our formula and we solve for speed, then RPM, let's just leave the 520 out, right, the other one out right now. Let's just look at torque and horsepower. So let's come up here and so we could say torque is equal to horsepower over RPM. Times 5252. Okay. So what it means is, if we're doing the same horsepower, right, you understand. Well, if RPM goes up, then what's going to happen to torque if horsepower is constant? It's on the bottom, guys. So if RPM goes up, then what's got to happen to torque? You can't, I can't say, let's say 25 is equal to, 250 divided by 10. Well, you're saying if I take this up to 20, this guy here is going to go up. Well, if I take that up to 20, 250 is a constant. If the bottom number goes up, then my answer's got to do what? Y'all understand what I'm saying? Yes or no? Okay. This is 25. Okay, so 25 is equal to 250 divided by 10. Okay, you understand that. Well, what if I bring this up to 20? Now you're saying, okay, a bigger number than 25 is equal to 250 divided by 20. It can't be. So if this bottom number goes up, what happens? What's got to happen to the number over here on the left? It's got to go down. So if speed goes up, torque's got to do what? Got to go down. If speed goes down, torque's got to do what? Go up. So we're going to use gears as a torque multiplier. But if I increase the torque on the output, the speed has got to go down. Y'all understand that? Yes or no? Right? Does that make sense? If the speeds go up, the torque's got to do what? Okay, so gear set is going to do one of two things. It's going to increase torque at a decreased speed, or it's going to decrease torque at an increased speed. Did I say that right? And this is what they're talking about, torque relative to power. So I'm transferring 3,450 horsepower. Right? You understand? And then here's my torque right here. Well, notice as speed goes up, so as speed goes down, torque does what? Yeah. And as speed goes up for the same horsepower, so inch pounds, inch pounds. I need to use the same unit. I'll fix that. So as speed goes down, torque goes up. As speed goes up, torque does what? So right here we're doing 1 horsepower. Which is roughly 746 watts of power per horsepower. Well, let me erase this on the right hand side if I can get to my pen. It's right there. So over there it's delivered that horsepower at 500 RPM. I get 126 pounds of torque. At 1,000 RPM, I get 63 pounds of torque. At 1,750, get 36 inch-pounds of torque. At 3 times 2,000, I get 32. So as the speed goes up, torque goes down, right? Does that make sense? So I can take a 1 horsepower motor and I can get 126 inch-pounds of torque out of that, but I've got to run it at a real slow speed. So our gears, if it steps up torque, it's going to decrease speed, right? You understand? If it does what? If it steps down torque, it's going to increase speed. So we use gears as either a torque multiplier or we do it as a speed multiplier, depending on what you need. Another thing we need to understand is the different loads we can put on the mechanical device. And this will become important later on for gears, but we have what we call radial loads. So a radial load would be a force placed on the axis, right? You understand? And then a actual load is a load placed parallel to the axis. Are we okay? That makes sense? So these are gears. So we're going to look at a gear video. And when I hook up my speaker, for some reason my microphone switches over to that. So
gears.
Can you hear this?
You'll find them in your engines, in your transmissions, in your shop tools, in your toys.
They're located in your garage, your shed, even your kitchen. But perhaps most importantly, you'll find them in your bicycle. Always remember, especially when driving your Prius, that the bicycle is the most efficient form of transportation that we have, fueled by simple things like Taco Bell and Mountain Dew. But anyway, let's learn physics. The basics, the most basics of gears, mechanical advantage, what's a torque multiplier, what's a speed multiplier. Two simple mesh gears. The big one is the input, driven by my hand, and the small one is the output. This is clearly a speed multiplier, because the output is moving faster than the input. Switch it up. The drive gear is the small one. The driven gear is the big one. It's moving slower, so this machine multiplies torque. When analyzing gears, first, just play with the system. Then, clearly identify which is the input, often called the drive, which is the output, often called the driven. We'll need to calculate a ratio. You can use either radius to radius, diameter to diameter, circumference to circumference, or, often very conveniently, the number of teeth to the number of teeth, because teeth represent circumference. So 36 teeth to 12 teeth, that little one is spinning 3 times as fast, 36 over 12. That's a mechanical advantage of 1/3. Here's a 36-tooth, 24-tooth combination, which means that the little one is spinning 1.5 times as fast, and the mechanical advantage is 2/3. Remember that any mechanical advantage less than 1 is a speed multiplier, and mechanical advantage greater than 1 in these cases is a torque multiplier. Note also the change in direction. If one turns clockwise, the other one turns counterclockwise, always with these enmeshed gears. Switch the input and the output, and you now have a speed divider. But more importantly, because it divides speed, it multiplies torque. So the output torque is going to be larger than the input torque. Mechanical advantage in this case, 36 over 24, 1.5. Now we're back to that 36-12 combination. Switch the input and the output, and you now have a torque multiplier. Clearly a speed divider identified visually. So it is a torque multiplier of 3. The mechanical advantage is 3. Note that a counterclockwise input gives you a clockwise output. It is still switching direction. So what do you do if you want to have them both spin in the same direction? One option is putting what we call an idler gear in between the two. You can see that both the input and the output are spinning clockwise, and the two shafts are now separated a larger distance. Now let's talk mechanical advantage and calculations. What's the number of turns? Output turns 1, output turns 2, and output turns 3. We know that that's a speed multiplier, torque divider. reminder, the mechanical advantage has to be less than 1, so it is 1/3. To get that value, the equation turns out to be the driven over the drive, the output over the input. And again, you can use circumference or diameter or the number of teeth or radius. And that right over here, crazy thing, doesn't even matter what size it is, because if you watch the output travels 1 rotation, output travels 2 rotations, output travels 3 rotations for 1 input, just as what we had before. Mechanical advantage equation is driven over drive. We'll be using the number of teeth. So 12 teeth, 24 teeth, and 36 teeth is what we have. So that 3-gear combination is 12 over 24, and then 24 over 36. The 24s end up canceling out. That middle gear size does not matter. The idler size does not matter. Another example. This one is a torque multiplier because it's a speed divider. And it takes 1.5 turns input for 1 turn of the output. So the mechanical advantage is 1.5 or 3/2 or 1.5. In addition to using an idler gear, there's another method we can use to make sure that the input and output are spinning in the same direction, and that is use a belt drive or a chain drive. Not only do the pulleys turn in the same direction, the system, compared to the idler pulley system, tends to be lighter, and you can place those shafts any distance apart as long as you have the proper length of chaining. Now let's find the mechanical advantage. First, you determine by looking at it whether or not it's a speed displacement multiplier or a force multiplier. Output is spinning faster, must be a speed multiplier. Therefore, the mechanical advantage is less than 1. Then you spin and spin and spin, and count the number of rotations. The input spins 11, output spins 14. Therefore, the mechanical advantage being less than 1 must be 11 over 14. In decimal form, that's about 0.79. Switch them, you get a torque multiplier, 14 over 11, or 1.27. One final example. This is called a whir gear, usually used for lifting heavy things. Just count input versus output. 1, 2, 3, just keep on going. Notice that this definitely does divide speed. Therefore, being a speed divider, it is a torque multiplier. And if you counted all those, you get 20. Mechanical advantage is 20. So absent friction, that machine would take your puny little input torque and multiply by 20. Gears, the basics. You just learned physics.
Yeah, it is. So, what did we learn? By the way, to figure gain, how much gain you get, the basic formula is gain is equal to out over in. And that's true over in. Right? You understand that? How much gain we get? How much gain do we get? So here we're dealing with drives, right? So here it's going to be driven over driver, right? And what can we use for the driven and the drive? What can we use to calculate these gains or these losses? If we end up with a fractional, it means it's a loss, right? If we end up with it, but then we got to figure out, okay, what do we use here? We can use the number of teeth. What else can we use? We could use circumference. What else could we use? We could use diameter. Or we could use a radius. These guys right here are proportional, so y'all understand. Yes or no? So, you know, like he said, I don't forgot he said, so, we got 36 teeth and 12 teeth. Right? You understand? So if we come over here and we say the gain is equal to the output, so let's say we're outputting 36, right? You understand? And then the driven, then what would we have? We would have a gain of 3. Now we got to figure out what to do with that speed. Okay. So what we have to remember is, okay, if torque goes up, speed goes down. If torque goes down, speed goes up. Okay. Y'all understand that? So since we're outputting on the big and bringing on the little, then this is a torque multiplier. Y'all understand that? Yes or no? If the little's on top and the big is on bottom, then it's a speed multiplier. Everybody understand that? So that means if I'm putting 9 inch-pound, I'm putting 9 inch-pounds in, I'll get 27 inch-pounds out. If I'm going at 200 RPM, then my output speed, RPM, would be equal to 200 divided by 3. So if torque goes up, speed goes down, right? That makes sense? You okay? Yes or no?
So big torque.
If we're outputting on the big gear and inputting on the little gear, then it's a speed multiplier. I'm sorry, did I say it right? If we're outputting on the big gear and inputting on the little gear, then it's a torque multiplier. If we're inputting on the big gear and outputting on the small gear, then it's a speed multiplier. But we're not changing horsepower. Y'all understand that? Yes or no? So power in equals power out. Power in equals power out. We can do it at a higher torque or we can do it at a higher speed. So your car's sitting perfectly still and you're trying to get your engine to move that big old car. What do you want? You want a torque multiplier or a speed multiplier? Torque multiplier. Now, once something's in motion, then it's going to take less torque to move it. So we want to go at a higher speed, right? You understand? So that's what your transmissions do, and it's switching gear ratios. It starts out with a real high ratio, right? You understand? And we want a torque multiplier, but eventually we're going to try it when we get up to 5th or 6th gear, depending on how many gears your car, then we're going to go to a speed multiplier. You understand that? And that's what your transmission in your car does. So these are the type of gears we're going to look at: spur gears, helical gears, bevel gears, and worm gears. And we're also ball and screw gears. And while we're going to look at ball and screw, I need to add that is that we have all these gears. I don't know if we got any spur gears or not, but we definitely got helical gears, and we got bevel gears and worm gears, and we've got what we call ball and screw gears, which I need to add that to the list. So this is a spur gear. And this is probably the most widely used gear. Now you don't know if this is a speed multiplier or a torque multiplier. Normally when we draw these things, we usually put a pinion or the driver on the left and the driven on the right. Now these are probably the most widely used gears out there because they're very simple to make. Very simple to machine. We just take a wheel and then we just either use a milling machine or a lathe machine, not a lathe, a milling machine to drill out the tip. Are you okay there? Notice a couple things we need to notice. If we don't use an idler gear, then the two are running opposite of each other. So they do change direction. Are we okay? Yes or no? The problem we have with these are pretty noisy. It's because of the way the gears, the face of the gear. So the face of the tooth is actually what's engaging with the other face of the other tooth. So the more area the faces are, the bigger the faces are, the more torque we can generate between the gear sets, right? That makes sense. These guys are real noisy. The other gear we have is what we call a helical gear. That's the one I give that name because it's at a slant. Usually when you use the term helical, that means at a slant. They're less noisy than spur gears, and we can get more torque because as soon as they put that thing at a slant, what happens to the face or the surface area, it gets bigger. But this is harder to machine because it's no longer at a straight line, it's at a curved line, right? That makes sense? We okay? Now the problem with helical gears is they generate radial torque. So them suckers, the way they're slanted and they're pushing on one side, they're constantly trying to push them apart, right? Or they create radial load. Are we okay? Then we have what we call a bevel gear. This is a helical gear. Two helical gears, I'm sorry. We have what we call a double helical gear and a herringbone. So double helical gears basically mounted with two helical gears on the same shaft. But notice the slant of the helical or the teeth are opposite of each other. Now what's that going to do? What's the advantage of these gears? Now these gears, especially these herringbone gears, these are pretty hard to machine. So what's the advantage of these two or more helical? Well, not necessarily speed. That's a good point. But why did we just say one of the biggest problems with a helical gear is? What? Well, yeah, they try to push each other. One of them's trying to push it this way. One of them's trying to push it this way. So these gears basically create actual loads. You understand? Yes or no? So you got one gear slanted this way and one gear slanted, you got one gear slanted this way, the other gear slanted that way. And what are they trying to do? They're trying to push each other apart, right? This guy's trying to push this one this way, and this guy's trying to push this way. So helical gears create a lot of actual load on the motors or whatever's trying to turn this. But if I come over here and do this, one of them's trying to push this way, the other one's trying to push that way, and what does it do? It basically eliminates actual torque. So the advantage of a herringbone gear or a double helix over a regular helix gear is that it eliminates actual torque. You understand? Yes or no? These are called bevel gears. Say about bevel gears. These can be helical bevel gears or they can be spur bevel gears. What they call straight bevel gears and spiral bevel gears. Let me get that out of the way. Why do we do these things? Why do we use these things for? But instead of the gears being like this, the gears can be at an angle, right? You understand that? So they don't have to be. So here on a spur gear or a helical gear, even a herringbone gear, the gears have to be parallel to each other. But let's say I'm trying to transmit it from here to here. We'll see a helical gear wouldn't work here, right? You understand? So what we'd have to do is we'd have to use some type of bevel gear to change the angle of what we're going from the driver to the driven, right? From the drive gear to the driven gear. So the bevel gear means that the two shafts do not have to be parallel to each other. They could be 90 degrees is probably the most popular, but that they don't have to. The slant of the gears can be varied to do almost any angle besides, right? You understand? Yes or no? Intersecting shafts. These are shafts that are not perpendicular to each other. I'm sorry, parallel to each other. Then we have the worm gear. So here we have on the worm gear, good. This is called the worm. Of course, this is the gear. Okay. Use transmitted motion between non-parallel and non-transmitted shaft. Depending on none of the teeth called single or double, the worm gear mostly used when speed and ratio is high. Speed to torque ratio. And we'll see these. They have different types of worm gears. And we'll look at this over there on the manufacturing line. I've got a video. I need to show that too. I need to find it. What they'll do a lot on the worm gear is they'll, I can't get to my marker. There we go. Is they'll take the worm or they'll take the gear, and can you see the way it's grooved down here? And what do they do that for? Well, the problem is if these two things were straight, and I need to put then, and this here is curved, then you'd only be making contact with very few teeth. But if we groove this thing and or put a channel down through it, then what that means is the worm can come in here and go further and engage more teeth. And then they'll also take the worm gear and it'll have a groove cut in it, like this. And then you have the worm, and then you have the teeth on the driven. And then this right here will be curved. And what we're trying to do is we're trying to get as many teeth on the worm in contact with as many teeth on the driven as we possibly can. So you'll see these worms, they'll have a groove cut into them. And then also the gear or the output gear will have a groove or channel cut into them to get a lot of contact with those teeth. So instead of just coming in here and trying to make all the force be carried by just a couple of teeth, right? You understand? And we'll see that. We can actually see this on these worm gears over here. So usually the gears are grooved, have a groove in them, and then the worm has a groove in them. So we can get as many teeth in contact with between the two gears to transfer a higher torque. And these guys can transfer a lot of torque. There's one we was looking at where the guys are opening up the doors on a canal system for the locks on the canal system. It's manual, so they pull their boat up there and they climb out of their boat and they get over there and start cranking that thing. But it takes a lot of cranks. You see them a while ago. It took 20 turns of the worm to get one turn out of the gear. Smaller gear is usually the pinion. The larger gear is called a gear. In most applications, the pinion is the driver. This produces speed that increases torque. Gear set is two gears meshed together. The driver transfers the torque and the speed to the driven. Of course, there's a lot of nomenclature inside the handout. Are we okay here? Any questions so far? Everybody okay? This is called an internal spur gear. Now, what advantage does an internal spur gear have over a regular spur gear? What's that? You're exactly right. It doesn't take as much space. If I was to take this same gear ratio and then come up here and it usually don't do this. So if I was to take these same two gears and come up here and put the okay, you understand that? So the advantage of an internal spur is that it takes up a lot of space, yeah. Okay. This is what we call a ball and screw gear. So what we're doing is we're taking a rotary motion, number one, and turning it into a linear motion. I understand that. So what happens is the screw actually turns, and when it starts turning, these ball bearings, of course, are in there to support the weight and give us a little friction as they start rolling. And then what happens, it goes into a tube and then comes back and fills in depending on which way the ball and screw runs. So the screw turns, and then whatever's mounted on this guy here moves in a linear motion. So we have one of these on the line over there, which I need to come over and put on. Okay? Can be bike driven and they cost. We have another method we can do this. It's called a rack and a pinion, where this would be the pinion gear, and then this one here would be the rack. And this is referred to as a rack and pinion. This is another technique we can use to take a rotary motion and convert it over to a linear motion. This is the method they used to use in automobiles. So this is the way they transferred it to your front wheel, the rack and pinion. I don't think we got a rack and pinion over there. But this is what you have to understand when you get gears. There's certain things you got to understand is that these two gears are going to have to mesh together. So what that means is the spacing between the gears and the width of the gap, and then of course the pitch of the face of the two gears have to match. That makes sense? Yes or no? Because if the gear teeth, if the spacing in the gear teeth, if the pitch and everything don't match, that means the gears are not going to mesh together real good. So we're not going to look at this. This is called a planetary gear. The advantage of this is we can get real high torque with a small display. We can do either, we can turn the outside and get a speed multiplier, or we can turn the inside and You can see why it's called planetary? Huh? Because of the, I don't need to know that, don't need to know that. So gearbox, also called a gear train. So why do we use gearboxes? Why don't we just have, if I want a torque multiplier, why don't we just have one little old gear and we have one big old gear? Well, if we wanted to get a real high torque multiplier, then, and then transfer a lot of torque, right? You understand that? Then we would end up with a gear set, 2 gears that would be extremely big. It'd take up a lot of space. So what we do is we divide, or they divide this down. So if this right here is my input shaft right here, so this is my input shaft, then notice this is turning a small gear, which turns a what? So what's that going to do? Is it going to increase speed or increase torque? Increase torque. Now this guy here is turning at, this small gear is turning at the same speed as this gear. So this is mounted on the same shaft. But now we have another little gear turning another big gear. So if this right here gives us a torque multiplier of 3, and then this right here gives us a torque multiplier of 4, what would be my total torque multiplier? Yeah. Yeah, 12. You multiply them together, right? Because they're, okay, you understand that. And then this is turning at the same speed, so we're not changing the speed, but the speed of this gear would be 1/12 of the input. So speed went down, torque does what? Go up. And then we take this one, and this is even a bigger gear. So let's say this is 5, then what would be my total torque multiplier? Yeah, my total torque would be 60, and my speed would be 1/60th of the input. That makes sense? But what we're doing is we're doing this with smaller gears, which occupy a lot smaller space. So that means if I did this with a regular gear, then this gear over here would have to be 60 times this gear right there. The diameter would have to be 60 times that gear right there if I try to do it with just one gear, right? You understand? So we do a lot of what we call gear trains or gearboxes, is what we call them out here. Let's use the gear train or gear sets. So these would be multiple sets, and this goes into a box or what we call a gear train. Okay? This is a typical transmission. And of course, what you're doing is when you're shifting, you're selecting your gear ratio, which is really neat. They kind of slide back and forth, and what you're doing is you're selecting gear ratios. But we got to have this guy right here. You don't understand why. So when you put your car in reverse, your motor don't change directions. Your motor always runs in the same direction, right? So the way the thing works is that the way it drives, as long as the motor's running this way, it would always move your wheels forward, right? You understand? But every one of these gears are going to reverse the rotation unless I put what between my drive and my driven? An idler. So this is what happens when you go to reverse. It switches that idler in. And I don't know which gear it uses. I think it uses first gear. You get a lot of torque in reverse, but you get a very low speed, right? Well, this is a typical 5-speed transmission. We're getting 6-speed transmissions now. It's pretty popular for vehicles. And motorcycles have had 6-speed transmissions for a long time. So here's my motor. And then we're running this through. So the first one's got 15 teeth, each teeth, something's got 45 teeth. Teeth are circumference that don't make any difference. This goes to 12, which goes to 48. So what would be is this a physique or gear peak? Very good. Okay. Would this be a speed, would this overall gear train be a speed multiplier or would it be a torque multiplier? Okay, so here I'm going little to big, here I'm going little to big. So anytime you go from little to big, you're a torque multiplier. When you go from big to little, it's a speed multiplier. Anybody ever well, of course, most of your bikes now are 15-speed bikes. And that's all you're doing on that bike is changing the radius of the sprockets, right? You understand? And if you ever notice, when you're on your low gears, your back sprocket is the biggest one. And the faster you go, the lower the sprocket gets off. If you start out on 15th gear, you can't hardly even turn the wheels. Because why? Because you can't create enough torque to turn that. So anytime we go from big to little, we get a speed multiplier. Anytime we go from little to big, we get a torque multiplier. So here's my motor right here. This is little, this is big. This is little, this is big. Right? You understand? Yes or no? So here we're going from little to big both times. Little to big. So these are torque multipliers. So what would be our how much would we multiply the torque? Huh? Well, we take out over in, so this right here would be 3. Now this is fed through a shaft right here, so this is multiplied by 3 right there. And what's this over here? This is 4. So what would my total multiplier be? 12. So my torque would be times 12, and my speed would be 112. Y'all understand that? So the reciprocal gives you what we multiply by to get the one that's slower, right? You understand? I guess that's what.
Looking at the small, that wouldn't be qualified as a small overview, like the 15 or whatever. That would be right there at 15.
What do you mean?
45.
No, it's out. So here's in. Here's my motor. So to figure gain, it's always out over in, no matter what system we're doing. So if I've got an amplifier and I'm putting 10 milliwatts in and getting 1 watt out, then what's the gain? It's going to be 1 watt divided by 10 milliwatts. So gain is always out over in, right? You understand? And of course, loss, if it comes up to be, and here, what we're doing is we're looking at gear ratios, and depends on what we're doing, depends on whether it's going to be a torque multiplier or it's going to be a speed multiplier. So here, when I come up with the 12, since this is a torque multiplier, why is it a torque multiplier? Because the out is the big gear and the in is the little gear. If the out is the big gear and the in is a little gear, then we're going to multiply torque and divide the speed. So that means if my input over here is running at 1200 RPM, then I would come over here and I'd say 1200 divided by 12. So what's the output going to be running at? It's going to be running at 100 revolutions per minute, right? You understand that? Yes or no? Is that right? 10 revolutions per minute. Oh, I'm sorry, 1,200. Yeah, 100 revolutions per minute. So what you do is you multiply by the number if it's, you multiply by the number depending on whether it's a speed multiplier or it's a torque multiplier. So those terms basically tell you what it is, right? You understand? So if I take a little gear and feed a big gear, right, you understand, then what's it going to do? It's going to divide speed and multiply torque. Well, that's like your car when you're sitting at a red light. Anybody ever drove a straight shift? Yes, y'all have never drove a straight shift. Well, you're responsible for shifting the gears. And you start off, your engine starts going high, and it's revving real high, and you're going 10 miles an hour. Because you're not multiplying speed, you're multiplying what? Torque. And then what do? In fact, you know, a lot of straight shifts have a tach gauge on. Because you can literally overspeed your engine. You can blow your motor up by overspeeding it, right? You understand? So your tach gauge is telling you where you have to shift. It don't mean you can't shift before then. But you're not supposed to shift after it. We call it red line. People that drive stock cars, they don't drive automatics because they want to control when the thing shifts. They don't want a computer determining when it shifts, right? And of course, if you ride a motorcycle, you're going to have to learn. A true motorcycle, you're going to have to learn how to shift gears. But you're controlling the gears, not some computer somewhere, right? Or used to, the gear shifts was controlled by vacuum. So it had a vacuum coming into your automatic transmission, and depending on how much vacuum your engine was pulling would depend on when the shifting occurred. Now it's all, your shift is done by electronics, trying to maintain the best gas mileage, torque gas mileage ratio. But if you want to do are we okay? Makes sense. So what do we use a clutch for? This is the next slide. What do we use clutches for? What do we use clutches for? What do you use clutches for? Nobody knows what we use clutches for. So you got there, when you stop, does your engine stop on your car? So your wheels are not turning. Your wheels are not turning, but your motor is. So what do we use clutches for? I don't know what we use clutches for. It allows us to stop this and not stop this. That's what a clutch does. And also we can use it to vary the torque. So a clutch basically slips. It allows slip to occur in the system. So it allows either the output to stop completely and then your prime mover does not stop. course, in a straight shift, you use it when you're standing at a red light. You got to have your clutch in. Why? You understand that? And then, of course, it allows us to shift between gears in the straight shift without stopping the prime move, which is pretty neat. So right now, if this output right here stopped, if this guy right here stopped, this guy here would have to stop. It would stall, right? You understand that? But, or something's going to tear up. So what a clutch does is basically it allows us to do what? Stop the output without stopping the prime move. So these are the clutches that are on the manufacturing line over there. We got several. And basically they're just plates that we mesh together. So your automatic transmission has got a what? Got a clutch. It's automatically controlled. In straight shift, so you control the clutch. So you got three pedals on a car that's got a straight shift in it. You got your gas, you got your brake, and you got your what? Your clutch. When you're stopped, what do you have to do? You have to push the clutch in. If you didn't push the clutch in, then what would happen to your motor? It'd stop. Right? You understand? It's like when you take off, I'm laughing because I flip my motorcycle over every time on its side. Luckily, I had highway bars on it. It hurt the bike. I was being towed, stalled my bike when I had my feet up on the highway pegs. I fell over. And it was a big motorcycle. Luckily, my brother-in-law was there. He come over and picked me up, or I'd have still been under that motorcycle. It didn't hurt me, but I couldn't get my leg out. And there's no way in the world I could pick that bike up. So what I did is, I didn't give the engine enough gas to create the torque, and the clutch and it just stalled the motor, and the motor. So this is adjustable, so we can actually adjust the torque that before the slip occurs, which is basically, so this would be what we call an adjustable or a slip clutch or adjustable. So what we have the ability to do is we can adjust this, and we can actually adjust the torque that gets through the clutch. We can either let no torque get through or a little bit get through. So if you ever drive a straight shift, that's learning how to use that clutch is really, because if you let the clutch all the way out, all odds are your engine's going to try to pick up all that torque instantly, right? You understand? Or you let it out slowly, and then you manage the torque transfer. My wife was trying to learn how to run a motorcycle, and she could drive a straight shift car, but what happens is all your timing moves up here to your hands. She never got it. So what does a bearing allow us to do? So what is a bearing? Y'all better take a break. We have several of these. We have several of these motors over there, and what these are DC motors that have the gear train built right onto them. And this is a servo motor. So a servo motor is a motor that provides feedback, and this is a servo mechanism on the back. This is called an incremental encoder. And then these are the two sensors. And what you should notice is one sensor is lined up on one set of grooves, and then the other sensor is lined up on the other set of grooves. So when the motor turns this direction, The inside one provides a pulse first, followed by the outside. And if it turns in this direction, then the outside provides a signal before the inside. So what the electronics can do is it knows which directions the motor's turning. And then each one of these guys would indicate a certain distance that the output shaft is rotating at. So this is the output shaft. This is the motor, which has the shaft that comes out the back. So the encoder is spinning at the same speed as the motor, and then it goes into the gearbox. And I don't know if this camera's going to pick it up or not. We'll try it. So this guy out here is rotating extremely fast. The motor's rotating extremely fast, and the shaft is moving very slow. So this is definitely what type of multiplier. So here's the output, here's the input. What? So this is the output, this is the input. Which one looks like it's turning faster? This looks like it's turning faster than this. Okay, is this turning slower than this? Then what is this? This is the output, this is the input. Is this a speed or a torque multiplier? Definitely a torque multiplier. And what I'm going to do is I'm going to pass this around, and if I go from this side, to that side, it's going to multiply speed. If I go from this side to that side, it's going to multiply torque. So I can come over here with my finger and I can spin that output, but I cannot come on this side and spin the input. I guess I can. It takes a lot of force. But just look at the difference, because what's going here, I'm going to a speed multiplier, right? You understand? So it's going to take more torque on this side than it is to turn that. Over here, this is a torque multiplier. Now this is a 65.5 to 1 ratio. So it takes 65.5 turns over here to get 1 turn over here. How do you understand that? Or this right here would be 1 over 65.5% of the speed that's over there. So this has a gearbox, this has a motor. Now what gears it's in there, I don't know. I think I got another one over there that I might take apart later on and see if we can actually see the gears. So what does a bearing allow us to do? Boy, if we wouldn't have bearings, we would be hurting. So does your car engine move? Well, how in the world are we transferring that rotating energy out back to your wheel? So we're going from something stationary to something in motion. I'm transferring energy from something stationary to something in motion. So we got to have the ability to transfer energy from something that's stationary over to something that's in motion. So the frame of that electric motor over there is not turning. The rotor is turning. But it's got to be mounted, that rotor has got to be mounted on something that is stationary. Right? You understand? So what these bearings do, it allows us to take something that's rotating and then mount it on something that's stationary, right? You understand that? So the responsibility of the bearing has got to take care of all your actual load. It's got to be able to handle the actual load, right? You understand? It's got to be able to handle a radial load. Radial load is the big thing. And of course, it's got to be able to carry the weight of what it's trying to transfer that energy through. And it's got to be very, very efficient. This bearing, of course, we call it a ball bearing. A device that is used to enable rotation or linear movement while reducing mechanical friction. resembles a wheel. Main function is to reduce friction and facilitate smoother rotation of an axis. From a stationary surface, I need to put that right. You understand that? So we got a plain bearing, we got a ball bearing, a roller bearing, a thrust